Shubham Shridhar Nadargi, Assistant Professor at Department of Mechanical Engineering, WIT, Solapur. Today we are going to discuss about boiling. At the end of this session, student will able to understand what is the distinction between boiling and evaporation process, classification of boiling process based on fluid state, and variation of heat flux during the phase change process. So, boiling is the phase change process in which the working fluid changes its state from liquid state to steam state. Boiling is happened during some critical condition. The necessary conditions for boiling process, if the temperature of the surface is greater than saturation temperature of the fluid at that pressure, then the boiling will takes place. So we are going to discuss about difference between boiling and evaporation process. If the critical conditions are, in case of critical conditions, if boiling needs to be considered, the temperature at the interface should be greater than or equal to saturation temperature of that at that particular pressure. And in case of evaporation takes place at normal condition, but in case of interface for the boiling always takes place at solid to liquid interface, and in case of evaporation, the interface between liquid state to vapor state. And in case of boiling, there is a formation of vapor bubble, and through that liquid medium the vapor bubble will disappear, and in case of evaporation there is no formation of vapor bubble. Boiling, based on state of fluid condition, there are two ways in which we can classify the boiling process. If the fluid is at stationary condition, that is considered under pool boiling. If the fluid is at motion condition, then it is considered to be in flow boiling. In case of swimming pool, it is, if we apply any nichrome platinum wire within that pool, we can consider it as a pool boiling condition. If the fluid motion is taking place with the help of any mechanical devices like pumps, in such case we can consider that flow as a flow boiling condition. In that pool boiling, we have two sub conditions, that is subcooled boiling and second one is saturated boiling. In subcooled boiling conditions, we have average temperature of fluid is lesser than saturation temperature of that fluid corresponding to particular pressure. If the average temperature of that fluid is greater than saturation temperature of that fluid at a particular pressure, then it is categorized under saturated boiling. Similarly, in case of flow boiling, we have two conditions as well. If the average fluid temperature is less than saturation temperature at that particular pressure, then it is considered as subcooled boiling. Similarly, we have average temperature. If we have average temperature greater than saturation temperature at that particular pressure, then it is categorized under saturated boiling. So the scientist Nukiyama conducted one experiment with the help of water and nichrome platinum wire. With the help of that, he came up with a graph between boiling heat flux and delta T excess. Delta T excess represent temperature of saturation and difference between temperature of saturation and the temperature of the wire. If the temperature difference is represented in the form of delta T excess, it is taken on x axis of that graph, and Q boiling, which is heat flux, taken on y axis of that graph. So this is the condition which represents boiling regime. On the basis of this, we can determine heat flux at a particular temperature during boiling process. If we see on the x-axis, we have 0 to 5 as a delta T axis. Within this domain, the average temperature of the fluid is less than saturation temperature. In such condition, we can consider the flow as natural convection. Because of density difference, the flow will take place, but rushing of the fluid is not dominant. That's why we can apply natural convection equation within this domain. From delta T excess 5 to 10, we can apply the boiling equation, because saturation temperature is reached in that fluid. So from delta T excess 5 to up to 30, we can consider this entire zone as nucleate boiling zone. In this, within 5 to 10, the vapor bubble formed near the surface of nichrome platinum wire will not reach the free surface. Hence, whatever the external pressure applied on that vapor bubble will try to burst that bubble. With bursting action, there is an immense amount of heat transfer immense heat mixing will take place. With that mixing, we can understand that heat transfer coefficient will increase. That's why the slope of the curve goes in strictly increasing manner. In case of delta T excess from 10 to 30, within that zone, whatever the vapor bubbles are formed on that nichrome platinum wire will reach the surface and burst. With this action, immense amount of heat mixing, fluid mixing will take place. Because of this fluid mixing, we can observe high heat transfer coefficient can be obtained. So the slope of this curve says heat transfer coefficient at delta T excess 10 to 30. If this heating action is continued between delta T 30 to delta T 10 100, within that zone, the vapor bubbles will form across that nichrome platinum wire. Will, because of low thermal conductivity of vapor bubbles, the conduction of heat from wire to the fluid is very low. Because of that only, the heat transfer will reduce drastically from delta T excess to 30 to 100. After that, the lowest point after delta T 100 shown is nothing but Leidenfrost point, which is very low heat flux for radiation regime. After delta T 100, the temperature difference between nichrome platinum wire and the adjacent fluid particles will be significant. In such cases, it is favorable for radiation to transfer the heat from one point to another point. Because of that reason only, the further increase in heat flux condition are shown. At the end of the diagram, which is at top right corner, we have one burnout point. If we increase the temperature after delta T excess equal to 1000, at that condition, the wire may burn out and damage may take place to our experiment. That's why we recommend to go for nucleate regime rather than radiation regime. This is the boiling regime for water. If apart from water any other fluid is taken, the shape of this boiling curve remains same. The magnitude will vary dependent on the fluid properties and the nichrome platinum surface conditions. Following are some of the references for heat transfer. The first one is Fundamentals of Heat and Mass Transfer by F. P. Incoprera and David P. Dewitt. And the second one is a textbook on heat transfer by S. P. Sukhatme sir. Thank you, students.